Yeah, this will be the final talk of the session, which means it's the final talk of the day, but it will be the last of the 6 half talks. So we have 2 speakers again.
Hopefully you should see a command line
ready
with
to set up?
critical errors at any time.
Can we have the beamer active this time before I try to sit down, because it never worked before?
Well, it's a Linux machine. It's not supposed to work, right? Okay, right, there we go.
This is the first one on the command line.
Yeah.
This looks nearly good.
Yeah, we just need to go into full screen mode. Yeah, there we go, but it's not. Okay.
I think you've nearly got it, so this stage is yours.
All right. Sorry? Presentations. There's this button. Thanks. All right. Well, hello, everyone. Maybe I'll stand here. Okay. Hello, everyone. It's good to, actually, it's good to be at the end, because we'll just do a loop back towards the beginning. There's some stuff that Brooklyn mentioned in our fantastic keynote this morning that we'd like to address, and we're here to do that. So, who are we? I'm George. I'm this guy on the right. Mirko is my co-presenter. I'll give him the mic soon. We're from the programming group, and we're kind of split over the University of St. Gallen and Darmstadt. And what do we want to do? We want to make safe and correct local first applications. And how do we want to do it? Using type systems and programming languages. And our projects are 2. There's 2 directions: consist, which Mirko will talk about, and then Propel, which is what I'll be talking about now. And Propel is just this verification tool that helps us in reasoning about any kind of stuff that does eventual consistency, but just essentially CRDTs, because these are the de facto ways of doing eventual consistency. And the verification tool just essentially tries to verify algebraic properties which the CRDTs care about. And these are commutativity, associativity, idempotency, and just we want to verify these properties. Propel is a DSL, but it's also a kind of a programming language. You'll see a bit towards the end. And the way it does these verification is by essentially restricting the type of functions to also annotate them with the algebraic properties that they're supposed to have. So here, for example, the very first function defines a merge function for the G counter. And the type says that it takes a list of 2 numbers and it gives out a list of numbers, but it should also be commutative, associative, and idempotent. And it does this by recursively traversing over the list and then applying pairwise maximum. So nothing very complicated there. And just for completeness, maxes all the way down with its own type. So essentially, the verification becomes part of the type checking, because if you want to have, if you want the type checker to accept this program, it also has to prove these algebraic properties. But the very cool thing about this program is that merge has this kind of traversal pattern, which is in Haskell world called like zip width. You just give it a function and it does pairwise elements on top of this list. And the very nice thing about it is that we can make it polymorphic over the properties. So if you give zip width any function that has the properties we want, then it produces a function with the properties that we also want. And so it kind of gave way into a new way of constructing correct CRDTs from ground up. Anyways, this is all kind of done, well, sort of done work. If you want to read more, go ahead, read our PLDI paper. But for those who have noticed, the properties that we check are kind of state-based CRDTs. So the novel stuff now is how do we deal with operation-based CRDTs? And, well, it's all about, again, commutativity, but this is a different kind of commutativity. The Propel commutativity is all the way down. And it's kind of different because, well, we quantify over 2 variables, not 1. And we talk about commutativity of arguments, not of functions. But luckily, we can encode one over the other in a way that's very nice for CRDTs, because we can just quantify over the messages that the operation-based CRDTs are supposed to handle. So if you do this kind of thing, where you map messages onto functions, and then you kind of use this ad hoc function all the way down, you can make one kind of commutativity equivalent to the other. So we wanted to try it. we took an operation-based map CRDT with last writer wins semantics, which famously is hard enough to merit a tweet and the publication by Martin. And and over many hours and many human labor, the bug was found. But so we said, okay, let's try to do it with Propel. So we wrote this code, which is essentially the same as the one that Martin tweeted. So I'll guide you through it line by line, not really. So it's full of comments, some standard library stuff. So this you wouldn't have to implement. The encoding of the CRDT and the actual message handlers. So it doesn't boil down to being all that much. And then 5 minutes later, after feeding it into Propel, we get this message, which means that we successfully failed to prove that it's correct. Right. So now I'll give you Mirko to talk about his project.
Yeah, thank you. Now we heard about correct CRDTs and eventual consistency, and now I want to go a bit beyond local first and start with this picture that we actually had in the talk in the morning, where we had different consistency models, and we said that well, local first applications kind of flow into the space of weak, what I call here weak consistency, which are consistency models that can have, where you can have temporary inconsistent replicas. But also, when you have an application, you might want to interact with stronger consistency models. So, right, so there's like this distinction between weak consistency, where changes are merged eventually, but sometimes you require some coordination. So, for example, when a client wants to authenticate to a server, they need to coordinate. But of course, the problem with strong consistency is availability, scalability. That's why when you want to write an app that kind of requires such an authentication, you only want the authentication to be strong consistent, while the rest of the app still should be weak consistent. So what we propose is called mixed consistency, which means that a program can consist of strong parts and of weak parts. And yeah, so now, but when you have an application of strong and weak parts, you actually have to reason about how these two parts interact with one another. So when we go back to this authentication example, let's assume that you have some credentials that are replicated with weak consistency. That means that a client and a server may see different user credentials. Now, when you have an authentication method that is strong consistent, then this authentication method could see different user credentials on the client and on the server. So this can lead to problems in the application. So we actually want to find such dependencies. So now, first of all, how would you create a mixed consistent application? So for example, you can choose different middleware. So you can store weak consistent data in one database and strong consistent data in another database. You can also use middleware where you can tune the consistency on a per operation or per transaction basis. The problem with that is you can't reason about the dependencies of the values in your program. That's why we are going to a language-based approach where you can actually track what you do with the values in your program and act accordingly. Right, so what do we have? We have replicated objects as a main abstractions. So replicated objects are just some objects that are available, exist on many devices. You can define a consistency level of these objects and of methods of the object according to what you want to do. You can bundle operations and transactions, which are atomic transactions, and in these transactions, we have a type system that prevents consistency violations. Yeah. So what have we seen in this talk? So we have seen some approaches to implement safe applications, one with Propel, which verify eventual consistency for CRDTs, and one with Consist, where we have saved mixed consistency in apps that go beyond local first. Yeah, and that's it with this talk, and we are ready for questions.
Immediate question here.
So both of these sound really cool. I'm curious, are they, like, what state are they in? Are they both like research projects or proof of concepts, or like ready to use in business logic, in production apps? And what do you see as like the path towards getting there if it's not there?
Yeah, so for my part, we have a prototype implementation, so it's not ready for industry usage or something. We are currently working a bit on a formalization and also some extensions to the language, but yeah, so it's a research project status currently.
Same goes for mine. But you can actually go on the website, there's a nice editor, and because everything is written in Scala, we compiled it to JavaScript. You can run the whole thing inside your browser, local first, and you won't upload any of your code, we won't read your code, but at the cost of running it in JavaScript, which takes like 10 times more. But yeah.
You mentioned dependencies. What kind of dependencies are you talking about? Like data?
Right, so basically data dependencies. So for example, when, like, I had this example with the authentication procedure, right? Where basically some data flows into this procedure that might be at a weaker consistency level that is actually needed for correct.
But you could also have operation dependencies, right? So one operation might make another operation available. There's this AMSA's paper work.
Right. So currently we are not looking at such dependencies, but only on data dependencies. But yeah, that's actually.
Thanks.
Yeah.
So great talk. I really enjoyed the ideas. So along the lines of getting that thing more into production, and I'm not sure what currently the view on academia is on TypeScript, but I was pretty, like when I got deeper into TypeScript and I have a little bit of Haskell background, I was like pretty surprised of like how many concepts from Scala and Haskell could be applied to TypeScript as well. And I think TypeScript is more used in a production setting. So I only encourage you to, if you get good feedback for this, and if you want to make it more production ready, I think this can be, a lot of those things can be applied to the type level of TypeScript.
We'll keep that in mind.
Yeah, but maybe just also to add, so I think the techniques should also apply still to TypeScript. A little bit on the architecture. So you might have seen two languages, one where it's like the Scala DSL, but we also kind of have this intermediary language. And then if we get access to like a TypeScript compiler, then we could just compile into this intermediary language. But that's kind of another project on its own.
We are in the process of psychologically accepting TypeScript. It's in progress. We are trying to do that.
I'm glad to hear that. So Guido speaks for his research group.
So
Yes.
Yep.
in the example of a transaction that may be dependent on some data that, say, hasn't arrived yet at a particular node and so can't run yet, is there an implementation of how consensus is found and like what form of strong consensus is used in the transaction, or like a technique that, or like, does the language implement a particular consensus algorithm, or how does it create transactions?
Right. So so currently what we are doing is we're using distributed logs, but so we are. the middleware that we are using for the language is kind of interchangeable. So currently we also have like 2 implementations. One on top of Akka and one on top of Cassandra. Yeah, basically we have an interface for middlewares that you could actually plug into the language. As I said, currently we only have a prototype for that, so that would be something to do also in the future.
Any further questions from the audience? So I know this worked way too well, so you don't. Well, I could ask about all the great properties of Scala, but I guess maybe because I also really want to answer this question a little bit. I think from a research perspective, it's like the concrete languages don't matter as much as the programming model used, and TypeScript or JavaScript even and Java have pretty similar semantics in some cases. So a lot of these techniques always apply to all of these like general purpose languages, right? Whereas a different language would be something like Datalog, where this probably would be very different, right? But for the other languages, it's a matter of implementation, which probably isn't that bad even. Any further questions from the audience? Otherwise, I think we're pretty much on time.
I was just going to ask if this is the most papers resulting from a tweet that anybody in the room knows about. 'Cause that's 2 now. Does anyone have a 3-paper tweet to their name? No? Okay, well, that's the record.
So this is yet to be published, the one based on the tweet.
Okay, well, Martin published his, so when you publish yours, that'll be the current record holder for this community.
For this particular tweet.
Yeah.
Oh.
There you go.
There might not be any after that, right?
Right, and that's saying there may not be more tweets for those on the stream. I guess they're X's now? I don't know what
Yes,
they're-
but I think this is an encouragement to the community to tweet more problems. So this way we can cite more tweets.
Yeah, I guess then thank you for the great talk. I have some closing words, but